Hello and welcome to the LEGO Lunatics Masterclass on our core code. I'm Coach Chris and this is going to be a fun way to learn our code, be able to explain to the judges what our code does, and make our robot game more consistent. Are you ready? Let's dive in. Okay, so here's what we're going to cover in this video. We're going to talk about what our core code is, the terminology we use when discussing our code, what our high-level code looks like, and then we'll dive into our Luni forward code. That's the code that takes the robot straight forward. That's all we'll have time for in this video, but I do hope to record more videos on our code next. So, what is our core code? As you can tell by this picture, it's a lot. Most of that space is taken up by comments to help you understand the code, but a lot of it is error handling code, the code that executes when the robot drifts off course. That's why we use this code, of course. We wanted our robot missions to be more consistent. This code is more consistent and, of course, longer and more complicated because of a few reasons. One, like our old smart drive code, it uses the gyro sensor to realize when it goes off course. Two, unlike our old code, it separates the turns from going straight or back to avoid that slipping of the wheels when you go around a turn. And three, this code accelerates and decelerates at configurable distances, which also helps avoid further tire slippage. Okay, so let's talk about some terminology. When I say mission, I'm talking about the group of code that executes after we push that button on the back of the robot for the program to start. When I say block, I mean a chunk of code in our Spike Prime app, like this yellow block here or these 4 red blocks. A run is one block of code that either goes straight forward or straight back. Here we have run 1 and run 2. A turn is, of course, a block of code that either turns left or right. An input is a configurable number you can set in your code, like speed or the angle you want the robot to turn. These 4 numbers here are inputs. And then last, there's something called a variable, which is also like a configurable number like the input here, but instead of setting it up in one of these blocks, you can set it up for an entire mission. All right, so here's what our code looks like at a high level. When you open the Lunatics core code file in Spike Prime, you should find your program start code up here in the top left, the Luni right for right turns, here's your left turns, here's your going forward, here's your reverse, and here's the big complicated code when you want to accelerate. We arranged it like this because we wanted the simplest code on the left and the most complicated code on the right. The Luni Accelerate is a more complicated version of Luni Forward. It's super consistent, but for short runs you might not need it. So let's start off with what your program looks like right in the beginning. You've got this when program starts yellow block. Whatever slot number you've chosen for your mission, that's usually in the bottom right of your Prime app. When you push the button with that number on the back of your robot, any code that's attached to this yellow block will execute. Most of our missions will simply be a series of runs and turns, but we will sometimes have attachments that also use the other 2 motors to lift or turn, or we'll use our color sensor to sense a color to figure out when we want to start or stop. Sometimes we'll have a separate line of code that executes when we use a message, but I'm not going to cover that in this video. So let's dive into the Luni forward code, the code that moves our robot straight forward. All right, first we created this code using the red My blocks in the Spike Prime. It looks kind of like this. These red blocks define our own block of code. We can write whatever we want, and we can use these configurable inputs like speed and distance here. These blocks can be found under My Blocks on the left side of your Spike Prime app, with the red circle on the left. Each of these red blocks and the code attached beneath it tells the robot how to move during one run. My Blocks allows you to write configurable code that can be reused in simple, short red blocks. You can see this long code here on the right is all just one line of code. Makes it really simple to set that in your code. So we've also, in this, we set the name, we called it Looney Forward. We created these little labels that tell us what these inputs are. So we said speed for the speed, and we said distance in degrees for distance. So those are our two inputs, speed and distance. It's how fast we want the robot to go forward and how far we want the robot to go forward. So speed is a number from 0 to 100. We normally recommend most missions being around 60 or 70. But if your robot is returning home and you don't care if it's perfectly straight, you can set it all the way to 100. And the distance is how far the robot will travel. We used to do centimeters in our code, and that's honestly preferable in a lot of ways, but this code uses degrees. The degrees are how many degrees you have in the wheel. So there's 360 degrees in a circle, so there's 360 degrees for this code. That would be one wheel rotation of our robot. Our robot had these big grippy wheels, so that's pretty far. It's actually 100 degrees per 6 centimeters. So you can also tell that these degrees will be very precise. It gives us a little bit more precision than we had when we just used centimeters. But there's another reason we're going to be using degrees instead of centimeters, and you'll see that in a little bit here. All right, Looney. So let's go ahead and add a couple blocks here onto our code. This is our high level My Block, and we have set the movement motors to A and B and set the movement motors to brake at stop. So setting the A and B is telling the robot that, hey, our movement motors are the front left wheel is A, the front right wheel is B. Those are the two motors. So that gives us it gives the robot an idea of what motors to turn when we're telling it to go a certain distance or turn left or right. And then setting the movement to brake just means that the motor will actually use power to brake when stopping instead of just coasting to a start or just stopping. And it applies friction to that motor afterwards. All right, let's add a couple more blocks on here. We're going to add the yellow weight block, and we're going to add this blue set the B motor's relative position. The wait block tells our code to wait 0.1 seconds before doing anything else. Why are we doing that? Because when you put the robot down on the table for the game and you push the button to run the mission, the robot might be slightly vibrating for just a fraction of a second, or maybe you've pushed off the table and the table shakes for a fraction of a second. By waiting, you're going to make sure your robot is absolutely still before it calibrates any of this code that's about to follow. And the next one that follows is setting the B motor to 0. So your motors always have a position that's known to the hub in our code. This block tells our code to set that position to 0 when we first run this block. Why? Because in the code below, we're going to always want to know the position of the motor to see how far the motor has turned, and therefore how far the robot has gone. All right, let's add a couple more blocks. We're going to set the yaw axis to the front, and we're going to set the yaw angle to 0. This set yaw axis to front is a new block for me that is setting the orientation of the gyro sensor. It's saying, hey, this is the front up here. The gyro sensor has 6 axes: front, back, top, down, left, or right. We're changing that axis so that it knows all the rest of the blocks are going to know this is front, and then we set y-angle to 0. 0 is telling our code that the direction the robot is currently facing is going to be 0. It's like telling the compass this is north. So because we want this run to be going straight, by setting the y-angle to 0, we'll let the robot know that if you get a -1 or a +1, you're drifting off course, and we're going to set some code to correct that. All right, now we're ready to add a repeat until block. This is the first real coding concept we've got here, and this is where the magic happens. This is the power. So repeat until block repeats everything inside these yellow, orange, black brackets, this top bracket and this bottom bracket. You see that little white arrow says, whoop, it's going right back up. It's going to repeat until everything inside this hexagon is true. So a hexagon value in this Spike Prime app means that it is anything that's returned from this is going to be either true or false. In coding, they call that Boolean, which usually returns a 0 or a 1, but that can also mean true or false. So this code is going to repeat until whatever is inside this hexagon shape is true. All right, so let's add some stuff to that. We're going to add a green operator block. Green blocks, the operator blocks, do math. This one is doing or, so this or this. Again, you see the hexagon shape. That means this is either true or false, or this is true or false. So I'm going to get a true or a false here. I'm going to get true or false here. If either of those are true, this will stop repeating. So that's what we're getting, this mathematical operator. We're getting two things that it could be true. So this code is basically saying, keep doing this until this or that is true. All right, let's add some more magic to it. Remember I talked about that, the position of the motor. Here we're saying, tell me what the motor is at now. What's the relative position now relative to where we set it earlier, which was 0? All right, so how far has the motor gone? You remember the input for our my block up above? We set 2, we set distance and speed. Here's the distance. We know we set it, let's say we set it for 100 degrees. If the B motor has gone more than 100 degrees, we've got the operator greater than, and we've got an operator equal to. If the position of the motor is greater than 100 degrees, this will be true, and this will stop repeating. Or if it's equal to 100 degrees, this will return true, and this will stop repeating. So that's what that means. Either it's true or false that the motor has moved more equal to or more than the distance set for this run. All right, let's see what this would look like in real life. In the right Boolean operator here, in the right green hexagon, our code would start off with our motor set at 0, right? That's what we set it at in the beginning. Let's say we want the distance to be 5, or just to make it simple. All right, the math would look like this. Currently, this is at 0, this is at 5, this is at 0, this is at 5. So this code says repeat until 0 is greater than 5, not true, or 0 is equal to 5, not true. So that returns a false. So this little arrow says, all right, let's go do it again. And inside this code, our robot is moving forward. We'll see what that code looks like in a minute, but just for now, know that it's moving forward. So let's say it moves forward just 1 degree. All right, is 1 greater than 5? No. Is 1 equal to 5? No. All right, move forward. 2, no. All right, 3, keep moving forward. 4, no. 5, oh wait, 5 is not greater than 5, that's false. But 5 is equal to 5, so that's true. So that returns a true. It exits this repeat loop, and we get to move on. So that's what this looks like. Now, we can set our first variable. All right, you remember what I said about variables? It's kind of like an input. It gives us some sort of numerical value. It's configurable. We can set it to different things. It's also global for our whole mission, so it can be changed over time. You can call a variable whatever you want to call it. We're going to call this one current error. So this variable, this little container that we can keep some number in that changes over time, we're going to call it current error. This, what we want to be, we want this current error to hold how far off the robot is from its current path. Let's say it bumped something, or somebody bumped the table, or it slipped on some dirt and it went off course. We want to know how far did it go off course. So we're going to set it equal to the yaw angle of the robot. Remember, we set yaw angle to 0 in the beginning when we pointed the robot straight at where we wanted it to go. That was the beginning of our mission. Now the robot's trundling along, it hit some dirt, it slipped off course, it slipped off of that 0, and this yaw angle, this blue circle here, will tell us what the current yaw angle is. It's not going to be 0 because it's off course. It could be -5, could be +5, could be 100, I don't know. Whatever it returns, it's going to, this variable current error is going to store that number for us. If you want to learn more about variables, there's a cool website called primelessons.org. They've got a great little PowerPoint on variables, but that's it at a high level. Okay, so now we've got a second variable called fix, and this variable needs to be proportional to the error. So if we knock the robot way off course, it needs to correct really big. If it's correcting itself and it's getting better, it needs to be a smaller correction. You'd think we could just set the correction equal to the error, right? But unfortunately, life's just not that way. That would look like the robot went off and then right back on. Unfortunately, there's physics and there's slipping and there's sliding. Like when you overcorrect with a car, you swerve back on until you get it straight, right? Same way with this. The error needs to be proportional. So at a high level, this code achieves this by subtracting the angle that the robot is off from one wheel's motor and adding that angle to the opposite wheel's motor. So it speeds up one wheel and slows down the other until it's back on track. You'll see that code a little bit further down when we get there. But for now, just know that that's what we're doing with this variable here called fix. Unfortunately, in order to understand the fix, there's going to be a third variable that we're going to have to create called previous error that tracks what the error was the last time we were off. If this is the first time this executes, that value will be 0. But if you had overcorrected, the robot needs to remember that overcorrection in order to slowly correct back onto course. So we are going to set this third variable, previous error, further down in the code, but we're just not there yet. I just had to explain that to you so that you understand how we're setting this second variable, fix. All right, so the fix variable, what it does here in this code is it multiplies the current angle the robot is off, that first variable that we created, current error, by -2, and adds that, right here, adds that to the last error we had minus the current error. Multiplying by 1 is just so that we can change that later to be for a different reason. This gives us that proportional number that we can subtract from one wheel and add it to the other. Okay, now that we've got those variables, we can actually make our robot move forward on a straight path. So we add this code, the start moving code, and you also can see that we've added the previous error variable that we talked about, and then we can finally exit this repeat until loop and stop moving. But what does start moving do? So start moving tells the left wheel to move a certain speed and the right wheel to move a certain speed. Basically, that's going to be 100% of whatever the speed is that we set in our my block above. But it's going to factor in the fix, that fix variable that we had, so that we'll course correct if the gyro sphere knows that the gyro sensor knows that we've gone off of our current target. So the left wheel will go at a certain speed, the right wheel will go at a different one based on whether it's the angle is a negative 5 degrees to the left or a positive 5 degrees to the right. This will tell the left wheel and the right wheel to go at that speed. It'll go faster or slower. Then that previous error variable tracks that previous error we mentioned in the angle that the robot corrected, and it'll slowly get back on course. And then once we've finally gone the distance we wanted to go, either equal to or greater than, the repeat loop will finally exit and the robot will stop moving. So what would that look like in real life? All right, let's say the robot drifts off course by just 2 degrees. And we set our robot to go at a speed of 50. So that would set our fix variable here. The current error is 2 degrees. It's multiplied by -2 plus 1 times the previous error is 0 in the beginning because there wasn't a previous error, minus -2. That equals -6. So the left wheel would be 50 minus -6, which equals 56. The left wheel would speed up, and the right wheel would be 50 plus -6, which is 44. The right wheel would slow down, and the robot would course correct. After course correcting, it would have a new yaw angle, hopefully 0, and then it would proceed straight. Probably slightly different, and it'll be back and forth until it's back on track. Okay, and that's how the Luni forward code works. You can now hopefully understand how your my block works. You understand that you can create your own code with those my blocks. 2, you know how your inputs work. You've got 2 inputs that you created in your Luni forward my block. You've got speed and distance. 3, you have used the B motor's position to track how far we've gone in degrees. Then 4, you've used the yaw angle. You've set that to 0, and you can use it to track whether our robot has drifted off of its straight course. 5, we've used a repeat until loop to see if we've gone the distance that we set in our my block, and if we haven't, it just keeps moving forward. 6, we created 3 variables to track the current angle of the robot. The angle we want our robot to proportionally adjust to, and whatever our last error was. And then finally, you have been using the start moving block to tell our left and right wheel motors to turn at the speed that we set, plus or minus any adjustment from our fix variable. And that's it. If you understand this, you have a solid foundation for moving on to understand the rest of our Lunatic core code. So I hope to be back soon with another video and show you all how that works. All right, thanks very much for watching, and good luck.